HPC environment. So the HPC is high performance computing, and we pretty much focus on parallelization of the things and trying to solve big problems faster. So I have this motivation video about a guy who's running a big simulation. Yeah, so this is what we're trying to achieve, to solve something that would take a couple of years in a few days. So I'm coming from the IT for Innovation, which is the supercomputing center in Czech Republic, and currently we are operating this one big machine, and we're going to have installed this smaller machine in a few months. So just to give you the idea what the supercomputer we're going to be talking about that we used for most of our experiments is a 1,000-node machine that is based on the Intel Xeon Haswell architecture. So the current one is the Skylake architecture. The Haswell was the previous generation. It has a fast network that would make it. That's actually what makes it a supercomputer. That's the fast network that has a 56 gigabits per second transfer rate between the nodes. So pretty much you can send 1 DVD per second between the nodes. And we also have we have half of the cluster is accelerated with this Intel Xeon Phi technology, which is pretty much the x86 accelerator with 61 cores, while these are 12 cores. The cores, it's 61 cores, but they are less, the performance slower, but you gain the performance by the parallelism. We're also going to have a new system, which is a small system, 200 nodes, but it's going to be based on the brand new architecture, the Cascade Lake. It will have a more memory per node, 192 gigabytes, and also we will have a faster network. So that's kind of, but most of the test and the work that has been done, it's for our current system, and this is the picture of it. And you can see it's been delivered by the SGI before it was bought by HPE. So if you want to do the distributed rendering with the Blender, you have the options. You have Blender Flamengo. It's kind of a web-based application that uses that you can set up a grid and pretty much send the frames. If you're rendering a movie, send each frame to a different node and parallelize it like that. So if you have multiple machines, you can distribute the rendering among those. But what we would like to do is go a little bit further, and pretty much what Milan is implementing as part of his PhD thesis is this as rendering as a service based on the Blender for the supercomputers. So we want to have a similar web or GUI. You can pretty much use the Blender as it is, as a control, as a client. Then it has, and we are pretty much developing this backend, which consists of the integration with the scheduler. That's the stuff that submit and schedule your jobs on the machine and handles that just one job runs on one machine at a time. And then the biggest work is on this Blender-based client that we use, and that's pretty much the backend of the entire rendering, and it's designed to handle the offline rendering, which is like the production rendering when each frame takes a couple of hours, but also for the interactive rendering, where you just want to eventually get to the rate to the performance close to 20 frames per second. And we also developed user plugins. It supports the user plugins that we use for the data processing. So I will show some examples. For example, the skeleton that's been in the introductory video that's been created by this plugin that takes the CT scan of from the hospital and just generates the model in the Blender. So one of the plugins that we are supported has been used to create that model. So what's our client did, which is actually most of the time I'm going to be talking about this backend because that's where the actual ray tracing is happening. So the client is based on the Blender cycles. It fully supports the Blender cycles, and it's has been extended to support what it's kind of a standard in the HPC. So if we have multi-core processor, we use the OpenMP, which kind of it's alternative to the pthread, so it's take care of the threading. If we need to solve one problem on multiple nodes, we use MPI, which stands for Message Passing Interface. So it's a library that helps you to send fast messages between the compute nodes. Then we also added the support for the accelerator, the Xeon Phi accelerator that we have. That's a 61-core x86 accelerator. We also worked on the integration of the Embry into the cycles and to support the different vector units. So you know that the Intel processors, how they gain the performance lately is just to increasing the vector units. So in a sense, each core can do, let's say, 4, 8, or 16 operations in every cycle if it can perform the same operation on a different data. So that's called the vectorization. So as these go high, it will give you higher vectors. So AVX it can work with the 8 floating points, and AVX 512 can work with 16 floating point numbers at the same time. So the client pretty much is designed in a way that, yes, you have a Blender, or if you want to use it on the tablet, we have a Unity client that's under development. So this is where you control what you want to render, and this is running in our data center. So this is the client that supports, as I said, both parallelization of the inside the compute node and MPI to parallelize on the multiple compute nodes. So each of these is a compute node. So mostly, yeah, these are the pictures. These are the benchmarks that we use for most of our tests, and these are the two machines that we're using. So as I have introduced one. That's the Salon machine at IT4I. So from that machine, we use the Haswell. And this is, if you are interested, this is the type of the Haswell. It's a Xeon E5 2680 V3. We use and then I'm just going to call it HSD or Haswell for the rest of the talk. Then we have the Intel Xeon Phi, the 61-core accelerator, and we're going to call it KNC. And in some tests, we have the GeForce GTX Titan X. We also have access. This is Italian supercomputer in Bologna. In a Cineca supercomputing center. They have a second generation of the Xeon Phi, and we're going to call it the KNL. And this is the latest Xeon that Intel is selling. This is the Skylake. So these are the architectures that I'm going to be using throughout the presentation for a different testing. So just to give you the idea of the performance of these different architectures. So this is pretty much these are the scenes. And this is the time in seconds that takes to render the exactly same scene with exactly the same resolution and number of samples and the settings. So you see, this gives you the idea how fast each architecture is. And the latest one, the Skylake and the KNL, those gives us the best performance. Of course, it's the latest architecture. So a significant amount of work that actually Milan did was to support different vectorization instructions. So for different BVH, the width of the BVH, you have BVH 2, 4, 8 up to 16. The different type of instructions are more useful. So for instance, if you need to process like the BVH 8, you need to have 8 floats processed at the same time. So you need at least the AVX. Or you can use the AVX 512, which can process 16 at the same time. So that the ideal BVH would be BVH 16 for the AVX 512 because it can process 16 floats at the same time. So porting to these different low-level optimization, that's been a work that we've mostly done. We also helped with the integration of the Embry into the Blender and also supporting the BVH for different instruction sets. And that's this optimization actually will lead to the results that you will see throughout my presentation. So now if we take a look at how the different width of the BVH, how it affects the performance, it's pretty significant for, so you have the architecture here. So now these are the Xeon Phi accelerators, the old one, KNC, and the new one, KNL. And you see that whether you use the BVH2 all the way to the Embry with the BVH8, it is a quite big difference in a performance that gives you the same, pretty much the same results. So, and this is on the KNC. Of course, the KNC is kind of the old architecture. Intel doesn't support it anymore. So the Embry, which actually is the Intel library, the latest version doesn't support the KNC, so we don't have the Embry results for the KNC. But for us, it's kind of important because we still have 800 of these accelerators in our machine, so we want to support it, because if we want to render something, we have this hardware and it's quite useful. It just needs some special attention. So, and this is the comparison of the regular CPUs. Again, this is the Skylake, the latest generation, and this is the previous generation, the Haswell. And again, you see how these, how the different BVH and additional using the Embry within the Blender, how it helps to reduce the processing time. So the Skylake and the Haswell has pretty much double the performance of their vector units. They went from 8 floats to 16 floats at the same time they can process, and that's pretty much what these help a lot. The other thing that actually, if we use the Blender client, which pretty much removes the pre-processing and the post-processing of the cycles and just performs the path tracing, we can export from the Blender, from the full-fledged Blender, we can export the scene for the cycles. And by exporting the scene, we can actually significantly reduce amount of memory that we need. So for instance, the one is rendering the open movie Spring, where the scene, if it's rendered in the Blender, it needs 47 gigabytes of the memory. If we just reduce the data that we need for the path tracing, for the cycles, we can get down all the way to 12 gigabytes of the memory. And as the accelerators that we have 16 gigabytes of memory, that's pretty much enables us to render the scene not on the CPU, but we can render it entirely on the accelerator because it fits to the 16 gigabytes of memory. But even if you have a render farm that most of your node has 32 or 64 gigabytes of the memory, and you have just few fat nodes that have 512 gigabytes of memory or 256, you can simply prepare the scene and just do the rendering on the nodes with significantly lower amount of memory to get the same results. And memory costs a lot these days. Yep. So when we were actually helping to render the Daily Dweeps movie, we've been testing different versions of the BVH with the support for the motion blur and without it. And we also tested the Embry that has the version that came with the motion blur support. And you see how these different versions behave for the movie as we go with the frames. And right now, this is probably not true in the latest version, but when there is a lot of particle systems, when this object is entering the scene, there has been some problems, but yeah, and that's been eventually solved out with the. So if we're coming back to the distributed rendering on the multiple nodes, if you want to do it over the cluster, so you have the native mode. That's how most of you use the Blender. You have a single machine, single workstation. Everything runs on that workstation. Then you can have what we call the MPI mode. That's where you run actually the Blender on our supercomputer. Let's say you have VNC and any remote desktop, and you run the Blender on our machines, and then from that one node where you have your GUI of the Blender, you just spread the workload to the other compute nodes. Or what the latest implementation that we have is actually that you can run the Blender on your workstation, and then it will just transfer the scene to our machine, and the rendering is happening back there, and you will just be getting the final pictures from back to your workstation. And this works for both final rendering, like the production rendering, as well as the interactive rendering. So you can get the interactive ray tracing if there is a couple hundreds machines sitting behind you if you want to, but it also with a significantly smaller number than that. So Blender, of course, if it renders on your workstation with the multiple cores, it supports the load balancing. So and it's mostly done with the tiles. So you have this tile stack. You either distribute the picture. We here distribute it by rows, but you can distribute it by rows and columns. So you get the tiles, and then if one core is finished, you just get a new work from the stack, and that's how it works. So you pretty much do the dynamic load balancing, and based on the scene, if one core gets the difficult part of the scene, the other one gets less difficult, it can render multiple at once. So we have the same for the distributed environment. So if we render a single frame on the multiple compute nodes, we have implemented the same. So we have so we can load balance multiple nodes. So if one node gets too difficult part of the scene, the other ones will render more tiles. And so you have either this dynamic, or you have this static, which pretty much just gives each node a stripe. So this is what we use for the production rendering, and this is what we use for the static for the interactive ray tracing. So if you do the interactive path tracing, you start with the fact that you just give each node the same a part of the picture. And what's actually is a work in progress is that dynamically as the interactive ray tracing is performing and you moving throughout the scene, we will have a load balancer that's pretty much going to shift these boundaries, so it will kind of help the balance between each of the compute nodes, even in the interactive mode. And this is pretty much just the idea how the dynamic load balancing actually helped if we were again rendering the spring movie. So, for example, in this case, the spring has been rendered just on the accelerators. We didn't use any servers. The entire scene was rendered just on the accelerators, and we've used 64 accelerators to render this single frame. So it's not one frame per accelerator. It's all 64 accelerators rendering single frame and then moving to another one. And you see that on average, it helps. It reduced the time by 2, but in some peaks it was even more efficient. So finally, just to give you the idea that it does work. So if we have a production rendering, but we render a single scene on 1 to 64 machines, we get pretty much a linear scaling. So. And this is rendered on our Salon machine. So the top line, slightly slower, is if we use just the servers. And then the bottom line is if we combine the performance of the servers as well as the accelerators. So we have, in each server, we have 2 Xeon CPUs and 2 accelerators. And the performance, it's kind of similar. So it reduces the time. If we use both CPU and the accelerators, we get double the performance. So this is for the production, for offline rendering, and the same thing we have for the interactive rendering. But here you have way more data transfers. You have to transfer every image to your client. You have to after every frame that you render one sample, you're going to transfer it to your client to make it interactive. So the scalability is not as perfect as it was in the previous case. So you see that after 8 nodes, it's losing, because this would be the ideal. The dashed line is the ideal scalability. But what you can do if you reach 25 frames per second, and you keep adding the nodes, you doesn't need to render one sample at 60 frames per second. You just can render 2 or 3 samples and maintain the 25 frames per second rate. So you still have interactive ray tracing at 25 frames per second, but you're sending the pictures with smaller amount of noise because you're having multiple samples for each pixel. So that's pretty much what's implemented. So if we reach 25 frames per second, we switch what we call from the strong scalability to the weak scalability. We add more work to each node. We also care about the energy. 2 minutes? Okay, it's gonna be. We also care about the energy. So we also tested the blender. So you know, at the computer, you can change the frequency of your processor. You can change the frequency of the memory. So what we eventually find out, if you care about the energy, you can slow down your rendering, let's say, by 20% and save 10% of the energy. So if you're not in the rush and you want to reduce your energy bill, this is the option. We've also tested different architectures and different cooling. So we have Haswell, which is air-cooled. We have Haswell, which is cooled by the direct liquid cooled. And we test the KNL. So in a sense, the KNL, just to give you a brief, there's a lot of figures. To give you the idea, the KNL pretty much is the one that is more energy efficient compared to the Haswell. So if you spend the money and you just want to use it, you think about the energy budget. Some architectures are better than the other ones to give you the same rendering time, but they render under, but the energy budget is lower. And yeah. Oh, I forgot the plugin. But anyway, so we also have some plugins. This is the medical plugin that's used to process the CT scans. We have a plugin for scientific visualization. So let's say this is the visualization of the airflow around the car. And we have a plugin for the virtual reality. And if you need more questions, I'm going to be here. You can ask. Thank you.